Hi, welcome back to Math 533, Topics in Euclidean Geometry, and welcome to the 12th week of the semester. This week, we're going to focus on broadly speaking, two topics. The first topic is we're going to look at the similarity theorems that we had from last time and wrap up those loose ends and prove a few of the things that we promised we'd do later. The other thing we're going to do is we're going to look at how similarity has consequences for properties of triangles. Okay, so the parts left over from last week, we have three things we want to do. We want to prove that a dilation is actually a similarity transformation. That's what we're going to do in this current video. And then in the next video, we will talk about the angle similarity theorem, and we'll talk a little bit about the side similarity theorem. Let's start with defining what a dilation is. So we fix a constant c that's positive and a point in the plane O. We say the dilation d of ratio c is the transformation that we define as follows. D of O is O. And for any x different from O, we define d of x. So here, this label with this colon with an equal sign means that we're defining x prime to be d of x. We define it to be the unique point on the ray OX, so that OX prime is that constant c times OX. So what do we need to prove? Right, we have a dilation, and for this I want to consider 2 points, A and B, and I want to see what happens to the segment AB under the dilation. So I have my center O, and I have my constant C, and I'm going to assume that C is less than 1. This is not a problem because if I have c larger than 1, I can look at the inverse of the dilation and work with that instead. Okay, so now we define A prime and B prime to be the images of A and B under the dilation. And we want to look at the segment AB and the segment A prime B prime. And what I want is I want the length of the segment A prime B prime to be c times the length of the segment AB. That's the defining property that we have for a similarity transformation. Okay, so by the definition of the dilation, it does scale correctly on the rays. So OA prime over OA is the constant c, and OB prime over OB is the constant c. And so now our theorem of Thales tells us that A prime B prime, the line A prime B prime, is parallel to the line AB. Actually, maybe we should review quickly what the theorem of Thales, also called the basic proportionality theorem, what it tells us. So here I have the configuration. We saw this last week, where I have 3 points O, A prime, and A on a line, and they're in that order. And then I have another line that intersects at O, and I have O, B prime, and B in that order on my second line. Then I consider these lines A prime, B prime, and AB. And what the theorem of Thales tells us is that these lines are parallel if and only if the ratio OA prime over OA is equal to the ratio OB prime over OB. In this video, because Thales is shorter than basic proportionality, I'm going to refer to it as the theorem of Thales. Okay, coming back to our proof now. We construct the line incident to B prime parallel to the line OA. So I've indicated that in green. And it intersects the segment AB in a point that I'm going to call M. Now, I'm going to apply the theorem of Thales now, where I think of B as being the intersection of the two lines, right? So I have the line BO and the line BA that intersect in B, and I have these parallel lines B prime M and OA. So now applying the theorem of Thales in that configuration, I get that BB prime over BO, right? So that BB prime over BO is equal to BM over BA. And so that's the opposite direction in the theorem of Thales, or the basic proportionality theorem. Now, by construction, I made A prime B prime MA to be a parallelogram, which means that the opposite sides are congruent. So AM is congruent to A prime B prime. And now I just play a game with algebra. So I say 1 minus C, well, 1 minus C, I can write that as OB over OB minus OB prime over OB. And then I collect that fraction on the same denominator. Right, and that's taking advantage of the fact that, right, if I look at OB minus OB prime, that's BB prime. And so I now collect that together. I use my parallelogram, I use this fact here from Thales to replace the ratio BB prime over OB by BM over AB. And then, right, BM, I can see it as being the distance BA minus the distance AM. So I just rewrite it like that. And then I break up my fraction. I get 1 minus AM over AB. And AM over AB, now replacing AM by A prime B prime from that parallelogram observation, I get 1 minus A prime B prime over AB. And right, so I have 1 minus C is 1 minus A prime B prime over AB. So I can basically solve that for A prime B prime over AB, and I get C, which is exactly what I wanted to prove. So that now proves that property I indicated in red here, which then shows that this dilation is indeed a similarity transformation with ratio C. Okay, now that we're done with our proof that a dilation is a similarity transformation, that's it for this video. Thank you for watching. I hope you enjoyed it. We'll catch you on the next one. Happy mathing.